9.1, day 2. Still talking about exponential growth, but now we're going to add in that a value. So what are some important characteristics of an exponential function? We'll get into some domain and range and do some more graphs with these. So exponential function again. So we're going to do two different graphs here. We're going to compare and contrast y equals 4 to the x, and then what happens if we have a 0.25 out in front of it, and just see how that looks. So let's go ahead and plug in these numbers. So if we have 4 to the negative 2, so I'm going to probably put this work on the outside over here. We'd have, so it's for this one over here. 4 to the negative 2 is the same thing as rewriting it as 1 over 4 squared to make it positive. Remember, we got to do that. So this is 1 over 16. 1 over 16. Squeeze it in there. What if we have negative 1 there? 4 to the negative 1. Flip that around. It's 1 over 4 to the first. That's 1 over 4. I'm going to kind of go a little faster this table a little bit. What if we have 4 to the 0? Anything to 0 power is 1. 4 to the first is 4. And then we have 4 squared, which is 16. Maybe you might see a little pattern here between the fractions that we have and then the whole numbers that we have. So if we were to plot this, well, first let's go ahead and do the other one. I'm going to change the colors. So I'm going to do this one. The only difference being now we're just multiplying by 0.25, or in other words, we're multiplying by 1/4. So we have 1/4 times whatever their answer was for this one, which is 1 over 16. That's 1 over 64. 0.25 times, or 1/4 times, where's our last answer here? 1/4. That's 1 over 16. All right, so we have 1 over 64, 1 over 16. Okay, we have 1/4 times, our last answer here was 1, so that's 1/4. Sorry, I'm trying to put this in there kind of sideways so it actually fits in the box. And then we have, plug in 4 here, or 1 here, which we already have is 4. So it's 1/4 times 4 to the first. You can put that over 1, and that would be 4 over 4, or 1. And the last one, we got 16. It's 1/4 times 16 over 1. So 16 over 4 is 4. Looks like this one's just kind of slightly behind the other one, so it kind of affects it in an interesting way. Okay, so let me try my best to graph this, and I'm going to graph the blue one first, the 0.25, 4 to the x. We're only going from -1 to +2. Okay, so maybe I'll spread this out. So I'll say this is -1, this is -2, and then 1, 2. So -2, it's 1/64. A dot at the bottom. I'm just going to put it right there at the bottom. And then at -1, it's 1/16. A little higher. And then at 0, it's 1/4. Right there, a little higher. At 1, it's 1. At 2, it's 4. 1, 2, 3, this would be 4. There we go. Now we'll connect our dots. All right, we'll go that way. Change the red color into the other one. So at -2, it's 1/16. So that actually is a bigger number, so it's slightly bigger than the blue. At -1, it's 1/4, which is also slightly bigger. At 0, it's 1. So they actually all the way go up to 1 here. At 1, it's 4. It's just a rough sketch as best we can. At 2, it's 16. So that would be 5, 6, 7, up to 7, 8, 9, 10. So it's way off the mark up here somewhere. Something like that. So what's different about the two graphs? Well, we could say a couple of things, like clearly this blue one is kind of going to be underneath. It doesn't grow as fast, right? This number out front made it go a little bit slower. So we can say the 0.25 makes the graph grow at a slower rate. Slower rate? Otherwise, they look the same, right? There really isn't much of a difference. It just looks like this one is going at a slower rate, and it's kind of a little bit behind it, and it's not, increasing as fast. I'm also going to show it to you on, it says go by 2s on the y-axis. I didn't do that. Oh well. I'm also going to show you what this looks like on Desmos, so let's do that real quick. Y equals, we'll do 4 to the x. There that is, and then we have y equals 0.25 times 4 to the x. There we go. And as you can see, is it color coded the same? It is. Red and blue. This looks exactly the same. So this one they're still increasing at a similar rate, but this one's just a little bit higher. So the one thing that is the same, we're getting the same exact shape. We're just messing with this beginning number here. And what this is, if you remember from before, this is the starting point. This is the a value. This is your y-intercept where it crosses the y-axis. So on this particular case, we know at 0.25, 1/4 is where it crosses the y-axis. So that's why at 0, it's 1/4, because that's 0.25. Whereas on this one, the front number out front you don't see is a 1. So it crosses the y-axis at 1. Okay, so let's do some characteristics and some definitions here. We have exponential curve. These are called exponential curves. It's just basically the shape of the graph. Specifically, we're talking about exponential growth. We are then going to move on to something called decay, but today is just growth. So what does that mean? As we increase x, then y subsequently also increases. So let me go back real quick. As you increase the x values from -2, -1, 0, 1, 2, you can clearly see all the y values are getting bigger on both of these. These are both exponential growth functions. All right, the only way that happens is if you have f of x equals a times b to the x, then if b is greater than 1, you get a growth. So that's this number right here. If that's bigger than 1, so we just did it with 4, right? This is a 4 here and a 4 here, the one with the x. If it's bigger than 1, it's going to be a growth, and it's always going to have this shape of growing up like that. Domain. The domain of these graphs, well, let's look at it. It goes forever this direction. We already talked about how there's an asymptote here, and it also goes forever this direction. It covers all x values, so we'll say the domain is all real numbers. Or you could say, remember, negative infinity to positive infinity. The range is a little different. It's kind of like the happy face parabola where it comes down and gets closer and closer to 0 here, but we know it never touches. It clearly doesn't go into this quadrant at all, or this quadrant. It's not in the negatives at all. So the range goes from 0, but not including 0, up to infinity. So we're going to say 0, but not including, which means you use parentheses, to infinity. These should look pretty familiar. It looks almost exactly like the domain and range of x squared. It's the same as this one for the domain, but the range for x squared, if you remember, that was a bracket, 0, infinity. So they're very similar as far as domain and range. The asymptote is located at, remember the line that it doesn't touch? That would be at the x-axis. Looking back at example 1, discuss with your partner, which we're obviously not going to discuss with the partner, what the x and y-intercept could be. So if you look at, let's do the y-intercept, that's pretty easy. The y-intercept always comes from the number out front, which we don't see one here, so it's 1. And then the y-intercept here is 0.25. Again, I already mentioned this in the table. It's right here, 1 and 0.25. That's a 0. And then when we talk about the x-intercept, where it crosses the x-axis, we basically already answered that. If there's an asymptote there, that means it never touches the x-axis, so there's none for both of these. NA, not happening. No x-intercept. Does not touch the x-axis. So there's a team huddle for you to try. Do an x-intercept, y-intercept growth factor. Just remember the x-intercept does not change. It is always, always not there. NA, not possible. The y-intercept is always the b value, which is here. Oh, I'm sorry. The a value. A value is the y-intercept, and then the b value is your growth factor. So if I were to try this one here, I would say none for this one. Y-intercept is the first part, 0.33. Growth factor is the number 4. Should be very easy answers for those 3. There's a couple more here. Domain and range also does not change, and neither does location and asymptote. So these answers will be all the same because they're both exponential functions. And then there's one graph for you to try as well. All right, we're going to do a word problem, and that'll be pretty much it. We can wrap it up. Example 2. When a new species is introduced to a new environment, it often has no natural predators and multiplies quickly. In 1859, 24 rabbits, that's pretty important, 24 rabbits were released into Australia for hunting. The rabbits reproduced so quickly that within 20 years, they were referred to as the gray carpet. We will assume that this single rabbit can populate an average of 3.5 rabbits per year. Now, a lot of people think that's crazy that you can have 3.5 rabbits per year, but because there's no 0.5 rabbits. But remember, this is an average. So that would be like one rabbit has three babies. Another rabbit has 4 babies. The average of that would be adding them together and dividing by 2. So that would be 7 over 2, which is 3.5. So you can have decimals when you have averages. You're adding together the whole number of rabbits divided by the number of parents, the moms. You get 3.5. So don't get freaked out by 3.5 here. Okay, so we're going to go back and use the formula that we originally had, the y equals a times b to the x. So I'm actually using this one back here, all the way back here. I'm just not using f of x, I'm using y. Is it better to use f of x? It doesn't matter. Yeah, we'll just use y. That's good. What's the initial value a? So how many rabbits were released? The initial value, the starting point. That's up here. 1859, it was 24 rabbits. So a is 24. We're basically going to build this equation. Determine the growth factor, b. That's how fast are they growing each year. That comes from up here, 3.5. So b is 3.5. C, what is the exponential function that would fit the situation? Well, we have a, we have b. We can fill this out. We have y equals 24 times, I'll put this in parentheses, you don't have to, you just put a dot there if you want, 3.5 to the x power. And that's our situation here. Starting point, we're starting with 24 rabbits, but every single year it increases 3.5 rabbits per year on average. All right, how many rabbits would there be in 1870? So really we have x is going to be number of years, and y is going to be number of rabbits. So we have the number of rabbits will be over here, and then this will be how many years it's been since they introduced the 24. So we're going from, what's the original entrance, 1859 to 1870. That would be 11 years. So our x value is going to be 11 years, right? So let's plug this in and put it into the calculator. So 24 times 3.5 to the 11th power. If you do this problem, you cannot multiply these two together. Exponents come first. So you have to do the exponent of 3.5 to the 11th power first. So if you do that, you get like 965,491. That's pretty big. Times 24. Looks like I got 27 million. That seems like a pretty big number. 23,171,797. So within the 11 years, we're going to have 23 million rabbits. I should put rabbits around there. There's a point here. You could either round that up or round it down. Doesn't matter. What is the first year the population of rabbits will hit over 3,000? So let's see how long that will take. I think I'm going to put that in Desmos, and it'll be easier to see it in the table. So let's see if that even works. Take this one out. So we have 24, 4 times 3.5 to the x. That's going to be a tough one to see. Look at that. It's really, really big. Okay, let's see if I can bring up a table. And then do some numbers here. So 3, 4, 5, 6, 7, 8, 9, 10, 11. See how fast that grows? Let's do it in exponential form now, or the scientific notation. So when did it hit 3,000? Somewhere between 3 and 4. Probably closer to the 4th year, like 3.5 or so. So I'm going to estimate it. So at 3 years, it was 1,029. 4 years, it's 3,601. But it's growing really, really fast. So let's do probably closer to 4, so maybe 3.5 years. Oh, what is the first year the population will hit over 3,000? So that would be year 4. Year 4. That's when it was 3,601. Okay, so the rest of the huddle is 2 word problems, which I might actually go through with you. Maybe I'll do this one. The speed of a supercomputer is measured in teraflops or trillions of floating point operations per second. In 2005, the Blue Gene/L computer recorded a speed of 280.6 teraflops. Over the last 30 years, the speed of the fastest computers has been growing about 78% per year. Suppose that this growth rate continues. We're going to let C of x equal the speed in teraflops of the fastest computer x years after 2005. Okay. So write a formula for C of x. So we're going to have C of x. It says, hint, since it increases 78%, the growth rate would be 1.78. So we're going from we're increasing it like 100% plus an extra 78%. So this is what we're going to use for our growth rate. So this would be equal, what's our starting amount? 280.6. And we're going 1.78 to the x power. So this would be A. Okay, it's not working at all. A, and this is B. For B, use your formula to predict how long it would take for the fastest computer to double the speed to double the Blue Gene record to 561.2. Okay. So let's see how long that's going to take. I think I'll put this in the table as well and see when it gets close to that. So let's go ahead and plug it into the calculator and see. Or you could also do like a guess and check, but I think I'm going to put it into the table here. So let's try y equals, what was it, 260? I can't remember. 280.6 times, I'll put in parentheses, 1.78 to the x power. All right. Where's that at? Okay, there it is. Get rid of these, bring up a table. So, how long will it take the fast computer to double the Blue Gene L record to 561.2? Well, it looks like it will be between the years 1 and 2, actually, so it won't take too long. So we'll say a little after the first year. A little over a year. Predict how many years it would take for the fast computer to hit 5,014 teraflops. Let's see. There it is, 5,014, so 5 years. It would take 5 years. So most of these answers you can get after you have the formula up here in part A. You can get the rest of it by using the table, either in Desmos or you can use the calculator at school. It would take about 5 years. And the way I do that in Desmos, if you want to see here, I mean, it keeps counting down. I'm just hitting enter and it gives you the next number. Or you could type in your own number if you thought you wanted to like see like, 15 or something. It's going to be a really big number. And so that's pretty much it. And you can finish up, do your own one-word problem and then the rest of Team Huddle for the first one. And don't forget to do the warm-up as well. That should be hopefully pretty easy to try. And try out number 3 here to turn all of that in to get full credit.